You're suspended in this void, and at first there seems to be nothing at all, just silence, just emptiness, just you in the dark. But wait, as your senses adjust, you begin to notice something. The faintest glow, not bright enough to see with your eyes, but it's there nonetheless. A whisper of warmth, a subtle presence filling every cubic inch of space around you. This glow comes from all directions at once. It has no source you can point to, no single star or galaxy generating it. It simply exists everywhere, always, like the universe itself is softly humming with an ancient song. This glow is real. It surrounds you right now as you listen to these words. It passes through your walls, through your body, through everything. It's called the cosmic microwave background, and it is quite literally the oldest light in the universe. These photons, these particles of light, have been traveling for more than 13 billion years. They began their journey when the universe was just 380,000 years old, when there were no stars yet, no galaxies, no planets. Nothing but a hot, dense fog of primordial matter cooling in the aftermath of the Big Bang. And here's what makes this truly extraordinary. We can see this light, we can measure it, we can map it across the entire sky, and in doing so, we can look back in time to witness the universe as it was in its infancy, capturing a snapshot of creation itself, frozen in these ancient photons. This is the story of that light, how we discovered it quite by accident, what it tells us about the birth and evolution of everything we know, and why it remains one of the most profound pieces of evidence we have for understanding our cosmic origins. Let me take you on a journey, not through space, but through time, back to a moment of accidental discovery that would change our understanding of existence itself. The accidental symphony. The year was 1964. Spring had arrived in New Jersey, bringing with it the usual sounds of renewal, birds singing, trees budding, life returning to the landscape after a harsh winter. But at Bell Telephone Laboratories in Holmdel, two radio astronomers were dealing with a problem that had nothing to do with the season and everything to do with an unexplained noise that simply would not go away. Penzias and Robert Wilson were not looking for ancient light from the beginning of time. They weren't cosmologists contemplating the origins of the universe. They were practical scientists who had been given access to a remarkable piece of equipment, a 20-foot horn-shaped antenna that had been built for satellite communications, but was now available for radio astronomy. The antenna was a marvel of engineering, constructed in 1959 for Bell Labs' Project Echo, an ambitious early communication satellite program that used giant aluminized balloons in orbit to bounce radio signals from one point on Earth to another. When newer satellite technologies made Echo obsolete, this exquisitely sensitive instrument became available for other purposes. The antenna itself was unusual in design. Unlike the dish-shaped radio telescopes you might picture, this was a horn antenna, shaped somewhat like an enormous megaphone or trumpet lying on its side. The horn shape was deliberate, engineered to minimize interference from the ground and from nearby structures. The sensitivity was extraordinary, capable of detecting signals so faint they would be lost in the noise of less carefully designed instruments. It was exactly what Penzias and Wilson needed for their planned research into radio emissions from the Milky Way. But there was this noise, this persistent, annoying static that cluttered their measurements. At first, they assumed it was coming from New York City. that sprawling urban landscape just over the horizon with all its radio and television stations, its electrical systems, its human-generated electromagnetic chaos. They pointed their antenna away from the city. The noise remained. They checked their equipment meticulously, testing every wire, every connection, every component. The noise persisted, stubbornly present in every measurement they took. Perhaps it was coming from the ground, they thought. They elevated their antenna, pointing it high above the horizon. The noise was still there. Maybe it was seasonal, they wondered, some artifact of atmospheric conditions or solar activity. They waited. Months passed. Summer turned to fall, fall to winter, winter to spring again. The noise never changed. It was there in the morning and there at midnight. It was there in summer and there in winter. It came from every direction. They pointed the antenna with exactly the same intensity. And then there were the pigeons. This detail always makes me smile because it's so perfectly human, so wonderfully mundane in the context of what would become one of the greatest discoveries in the history of science. Pigeons had taken up residence inside the horn antenna. They nested there, finding the metal structure a convenient and sheltered place to roost. And where pigeons nest, they leave behind what Penzias would later politely refer to as a white dielectric material. In other words, bird droppings. Lots of them. Surely the two scientists thought this must be the source of the mysterious noise, the accumulated deposits of pigeon residents coating the inside of their precision instrument. They constructed a pigeon trap, carefully captured the birds, and released them miles away. They spent hours, perhaps days, painstakingly cleaning every surface inside the antenna, removing every trace of the bird's occupation. They reassembled everything, recalibrated their equipment, and ran their measurements again. The noise was still there, exactly the same, unchanged, undiminished, coming from everywhere at once. By this time, it was early 1965, and Penzias and Wilson were genuinely perplexed. They had eliminated every source they could think of. They had checked and rechecked their equipment. They had accounted for every possible terrestrial or instrumental explanation. What they were left with was a signal with a wavelength of 7.35 centimeters, corresponding to what they measured as roughly 3.5 degrees Kelvin, a temperature just a few degrees above absolute zero. It was uniform across the sky, present day and night, unchanging with the seasons. It seemed to be coming from the universe itself. At the same time, just 60 kilometers away at Princeton University, a group of physicists led by Robert Dicke was preparing to search for exactly this kind of radiation. They had been working through the theoretical implications of the Big Bang model, following calculations that had been made in the late 1940s by physicists George Gamow, Ralph Alpher, and Robert Herman. These earlier theorists had predicted that if the universe had indeed begun in a hot, dense state and had been expanding ever since, there should be remnant radiation from that early epoch, now cooled by billions of years of cosmic expansion to a temperature of just a few degrees above absolute zero. Dicke and his team were building equipment to search for this cosmic background radiation. They were months away from being ready to make their measurements, and then through a friend at MIT named Bernard Burke, Penzias learned about this theoretical work. He called Dicke at Princeton and described the mysterious noise they had been detecting. Dick listened. When he hung up the phone, he turned to his colleagues and said, "Boys, we've been scooped." The pieces fell into place rapidly after that. Dicke and his team, including theorist James Peebles, came to Bell Labs to examine the antenna and listen to the signal. The characteristics matched their predictions almost perfectly. Penzias and Wilson had accidentally discovered the cosmic microwave background radiation, the afterglow of the Big Bang itself, the oldest light in the universe, filling all of space with its faint but persistent glow. They published their findings in July of 1965. The paper had one of the most understated titles in the history of physics. A measurement of excess antenna temperature at 4,080 megacycles per second. Hidden behind those mundane technical words was a discovery that would transform cosmology from a field of philosophical speculation into a precision science. It was direct observational evidence that the universe had a beginning, that it had evolved from a hot, dense state, that the Big Bang Theory was not just mathematical abstraction, but physical reality. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for their discovery. The Swedish Academy wrote that their work had given humanity the ability to obtain information about cosmic processes that took place some 14 billion years ago. A happy accident involving pigeons and a repurposed antenna had opened a window to the dawn of time itself. But what exactly had they discovered? What is this cosmic microwave background, this ancient light that surrounds us? To understand that, we need to explore the nature of this radiation and what it represents. What is this ancient light? Imagine, if you will, that the universe is an enormous concert hall, and playing constantly in this hall is a single note. Not a note you can hear with your ears, but one that exists in a different part of the spectrum of electromagnetic radiation. This note has been playing for more than 13 billion years, and it will continue playing for billions more. It fills every corner of space, every gap between galaxies, every void in the cosmic web. You cannot escape it. Wherever you go in the observable universe, this note is there, this background hum, this fundamental frequency of existence. This is the cosmic microwave background. It's not a thing in space, not an object you could point to or visit. It's a property of space itself, a bath of radiation that permeates the entire universe. At any given point in space, there are roughly 400 photons from the cosmic microwave background in every cubic centimeter. That's 400 in a space smaller than a sugar cube. All around you, right now, billions upon billions of these ancient photons are passing through your body every second, carrying information from a time before stars existed. The temperature of this radiation is extraordinarily cold, 2.72548 Kelvin to be precise, though we often round it to 2.7 Kelvin for simplicity. This is just 2.7 degrees above absolute zero, the coldest temperature theoretically possible in our universe. Absolute zero, remember, is minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. So we're talking about radiation that is almost incomprehensibly cold, hovering just barely above the point where all molecular motion would cease. Because it's so cold, this radiation exists in the microwave portion of the electromagnetic spectrum. That's the same part of the spectrum used by microwave ovens and cell phones, with wavelengths measured in millimeters. The peak wavelength of the cosmic microwave background is about 1 millimeter, right in the middle of the microwave range. This is why we can't see it with our eyes. Our eyes are sensitive to visible light with wavelengths between about 400 and 700 nanometers. The CMB's wavelength is roughly 2,000 times longer than visible light. To our eyes, the universe appears dark between the stars, but if we could see in microwaves, the entire sky would glow with a nearly uniform light. And what makes this radiation truly special is its spectrum. When physicists measured the cosmic microwave background carefully, they found that it follows what's called a black body spectrum with extraordinary precision. A black body is an idealized object that absorbs all radiation that falls on it and re-emits that radiation in a very specific way that depends only on its temperature. It's called a black body because it absorbs everything, appearing perfectly black in the process, but the radiation it emits has a characteristic distribution of wavelengths. The cosmic microwave background has the most perfect black body spectrum ever measured in nature. When scientists plot the intensity of the CMB at different wavelengths, the curve they get matches the theoretical black body curve so precisely that you literally cannot see the difference between the data points and the prediction. This is extraordinary. The universe in its infancy was in nearly perfect thermal equilibrium, with matter and radiation exchanging energy so efficiently that they reached the same temperature everywhere. The CMB preserves this perfection, frozen into its spectrum by the expansion of the universe. This brings us to an astonishing fact. The total energy contained in the cosmic microwave background exceeds the total energy of all the light emitted by all the stars in all the galaxies throughout the entire history of the universe. Think about that for a moment. Every star that has ever shone, every supernova that has ever exploded, every quasar that has ever blazed across billions of light years, all of that combined is less than the energy still present in this faint microwave glow filling empty space. The universe began with an enormous amount of thermal energy, and even after more than 13 billion years of expansion and cooling, the remnant of that primordial heat still outshines everything that came after. Before cable television became ubiquitous, when TVs relied on antenna signals, you could actually see the cosmic microwave background. If you tuned your television to a channel that wasn't broadcasting anything, you'd see static on the screen, that familiar snow of white and black dots dancing randomly. About 1% of that static was caused by photons from the cosmic microwave background hitting the television's antenna. You were seeing the afterglow of the Big Bang mixed in with the other electromagnetic noise. How extraordinary is that? The oldest light in the universe showing up as noise on your TV screen. But here's what makes the cosmic microwave background most remarkable of all. It's not quite perfectly uniform. If it were, it would tell us that the early universe was completely smooth and featureless, which would present a serious problem. How would galaxies, stars, and planets have formed from a perfectly uniform distribution of matter? There would be no density variations to serve as seeds for gravitational collapse, no slight irregularities to grow into the rich cosmic structure we see today. Fortunately, the CMB is not perfectly uniform. It has tiny temperature variations, fluctuations of only about 1 part in 100,000. In some directions, the cosmic microwave background is slightly warmer, about 30 millionths of a degree warmer. In other directions, it's slightly cooler by the same amount. These variations are incredibly small, almost impossibly subtle, and yet they're there, written into the fabric of the ancient light, carrying information about the structure of the universe when it was less than 400,000 years old. These tiny ripples in the temperature of the cosmic microwave background are like cosmic fossils, preserving the imprint of density variations in the primordial plasma. The slightly warmer spots correspond to regions that were slightly denser, containing a bit more matter than average. The slightly cooler spots correspond to regions that were slightly less dense. These density variations were tiny at the time, but they were enough. Over hundreds of millions of years, gravity amplified them. The dense regions grew denser, attracting more matter. The underdense regions grew emptier, losing matter to their denser neighbors. Eventually, the dense regions collapsed to form the first stars, then galaxies, then clusters of galaxies, then the vast cosmic web of structure that fills the universe today. When we look at a map of the cosmic microwave background, we're seeing the seeds of everything that exists. Every galaxy, every star, every planet, every atom in your body can trace its history back to those tiny fluctuations in the temperature and density of the primordial universe. The ancient light carries that story, broadcasting it across the cosmos for anyone with the right instruments to receive. But to truly understand what the cosmic microwave background represents, we need to go back further in time, back to the moment when this light was created. We need to understand the conditions in the early universe, the processes that gave birth to these photons, and the extraordinary event that set them free to travel across billions of light years to reach us today. A universe of fire and fog. Travel back with me in your imagination to a time 13.8 billion years ago. Not long after time itself began, not long after space itself came into existence. The universe is unimaginably small, incredibly hot, and almost incomprehensibly dense. If you could somehow exist at this moment, if you could experience it with senses adapted to perceive such conditions, you would find yourself in something resembling the heart of a star, but far more extreme, far more violent, far more energetic than any stellar interior could ever be. Try to imagine the intensity of this environment. Every cubic centimeter of space is packed with energy at densities that would seem impossible by the standards of anything we encounter in today's universe. The matter and radiation are so tightly coupled, so intensely interacting, that they form a single unified fluid, neither purely matter nor purely energy, but something in between, a state of being that exists nowhere in the universe today, except perhaps fleetingly in the most extreme astrophysical events. The temperature is roughly 273 million degrees above absolute zero. To put that in perspective, the surface of our sun is about 6,000 degrees. The core of the sun, where nuclear fusion converts hydrogen to helium, is about 15 million degrees. The early universe, everywhere all at once, was nearly 20 times hotter than the core of the sun. At this temperature, matter as we know it cannot exist. There are no atoms, no molecules, no solid or liquid or even gaseous forms of matter in the conventional sense. Instead, the universe is a roiling plasma, a sea of subatomic particles in constant violent motion. There are electrons, negatively charged particles so light and energetic at this temperature that they zip around at nearly the speed of light. There are protons, the positively charged nuclei of hydrogen atoms, though they cannot capture electrons at this temperature to form actual atoms. There are atomic nuclei of helium and trace amounts of lithium formed in the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis. And there are photons, particles of light, so numerous and so energetic that they outnumber the matter particles by about 1,000,000,000 to 1. The photons and the matter are locked together in an intricate dance. The photons cannot travel far before they collide with an electron. This collision is called Thomson scattering, named after the physicist J.J. Thomson, who first described the process. When a photon strikes an electron, it bounces off, changing direction but not losing much energy. The electron recoils slightly from the impact but remains free, not bound to any atomic nucleus. Then another photon strikes the electron, and another and another. Meanwhile, the photons themselves are constantly being absorbed and re-emitted by the matter, exchanging energy, maintaining thermal equilibrium. What does this mean in practical terms? It means the early universe is opaque, completely opaque. If you tried to shine a light through this primordial plasma, it wouldn't get far. The photons would scatter off electrons almost immediately, ping-ponging from one electron to another in a chaotic, random walk. The mean free path of a photon, the average distance it could travel before scattering, is extraordinarily short, perhaps less than the width of an atom in today's universe, though distances are different when space itself is expanding and the universe is so much smaller. This opacity creates what physicists call a photon barrier. We cannot see through it. We cannot use light to probe the universe before this epoch because the light gets scattered and scrambled and thermalized, all information about its origin erased by countless interactions with the plasma. It's like trying to see through thick fog or dense smoke. The light is there, bouncing around inside, but it cannot escape. It cannot carry information from one place to another. The universe is, in a very real sense, dark, not because there's no light, but because the light cannot travel freely. As the universe expands, though, it cools. This is a fundamental consequence of expansion. Think of it like releasing compressed air from a tire. As the air expands into a larger volume, it cools. The universe does the same thing, but on the largest scale imaginable. Every cubic meter of space becomes larger, and as it does, the energy density within it decreases. The temperature drops. This cooling is relentless and universal. Everywhere in the universe, simultaneously, the temperature is decreasing as space expands. The rate of cooling depends on the expansion rate, which in turn depends on the total energy density of the universe, including matter, radiation, and any other forms of energy present. In the early universe, radiation dominates. The energy in photons exceeds the energy in matter particles, and this radiation-dominated universe expands in a very specific way that causes the temperature to drop as the inverse of the universe's size. If the universe doubles in size, the temperature drops by half. If it expands by a factor of 1,000, the temperature drops by a factor of 1,000. And so, over tens of thousands of years, the temperature falls from hundreds of millions of degrees to millions of degrees. from millions of degrees to tens of thousands of degrees. The universe is still extraordinarily hot by any human standard, still a plasma of free electrons and atomic nuclei, still opaque to light, but it's cooling gradually and inexorably, heading toward a critical threshold. That threshold is about 3,000 degrees Kelvin. This is the temperature at which something remarkable happens. At 3,000 Kelvin, the thermal energy of particles in the plasma drops low enough that electrons and protons can bind together to form neutral hydrogen atoms without being immediately broken apart again by collisions with photons or other particles. The ionization energy of hydrogen, the energy needed to tear an electron away from a proton, is about 13.6 electron volts. At 3,000 Kelvin, the average thermal energy is about a quarter of an electron volt, much less than the ionization energy, which means that once an electron and a proton combine, they're likely to stay combined. This is the moment the universe has been building toward. This is when everything changes. This is when the fog lifts and the universe becomes transparent, when the photons trapped for hundreds of thousands of years in endless collisions with electrons are suddenly set free to travel across the cosmos. This moment has a name. Actually, it has several names, each capturing a different aspect of what happens. Physicists call it recombination or decoupling or the surface of last scattering. Each name tells part of the story. The moment of liberation. 380,000 years after the Big Bang, the universe reaches its moment of transformation. The temperature has dropped to about 3,000 Kelvin. The time has come for electrons and protons to unite, to form the first neutral atoms, to create matter as we would recognize it if we could touch it or hold it. This moment, this transition from plasma to neutral gas, is one of the most important events in cosmic history, and understanding it is key to understanding the cosmic microwave background. Picture the scene if you can. The universe at this epoch is still quite hot by everyday standards, roughly half the temperature of the surface of the sun, but cool enough that chemical bonds can begin to form. Everywhere, simultaneously across the entire observable universe and beyond, electrons and protons are finding each other, attracted by their opposite electric charges, combining to form the simplest and most abundant atom in the universe, hydrogen. It's not a violent process. There are no explosions, no dramatic releases of energy. It's gentle, almost quiet, a gradual transition as the universe crosses a critical threshold. The term recombination is actually a bit misleading, though it's stuck in the physics literature. Recombination implies that electrons and protons are combining again, that they had been together before and are now reuniting. But in reality, this is the first time in the universe's history that stable neutral atoms are forming. In the very earliest moments after the Big Bang, before even Big Bang nucleosynthesis, the universe was far too hot for any stable structures at all. Then, for hundreds of thousands of years, it was too hot for neutral atoms. So this isn't technically a recombination. It's just combination the first time it's happening. But the name has stuck, perhaps because it sounds better, or perhaps just because of historical accident. A more descriptive term is decoupling. Before this moment, matter and radiation are coupled together. The photons and the electrons interact so frequently through Thomson scattering that they move together like a single unified fluid. The photons can't travel independently. The electrons are constantly being pushed and pulled by photon interactions. They're locked together in thermal equilibrium at the same temperature, exchanging energy efficiently. But when electrons combine with protons to form neutral hydrogen, everything changes. Neutral hydrogen atoms are transparent to photons at these energies. A photon can pass right through a hydrogen atom without interacting with it, at least most of the time. There are specific wavelengths where hydrogen absorbs light, those famous spectral lines that astronomers use to identify hydrogen in stars and gas clouds. But for the vast majority of photons in the cosmic microwave background, neutral hydrogen is essentially invisible. It doesn't scatter them, it doesn't absorb them, it just lets them pass by undisturbed. This means that when the electrons combine with protons, the photons suddenly have no one to interact with. In the span of perhaps a few thousand years, maybe even faster, the universe transitions from opaque to transparent. The mean free path of photons, which had been extraordinarily short, suddenly becomes enormous, larger than the entire observable universe. The photons simply travel in straight lines, carrying their energy with them unimpeded by matter. This is decoupling. The photons decouple from the matter. They stop exchanging energy with electrons. They maintain whatever temperature they had at the moment of decoupling, but now that temperature drops only because of the expansion of space, not because of interactions with matter. The universe becomes transparent, and the photons begin their long journey through time and space. The third term for this moment is the surface of last scattering. This name comes from thinking about the event from our perspective, observing it billions of years later. Imagine the universe at the moment of recombination as a thin spherical shell surrounding us, located at exactly the right distance so that photons leaving that shell at the moment it became transparent are just now arriving at Earth. This shell is the surface of last scattering. It's the last time and place where the photons we observe today scattered off electrons before traveling freely through space. The surface of last scattering isn't a physical surface, of course. It's not a boundary you could touch or a wall you could see. It's a conceptual surface defined by geometry and the speed of light. Every observer in the universe sees their own surface of last scattering, a sphere centered on themselves at a radius of about 46 billion light-years in today's expanded universe. The photons coming from that surface, the ones we detect as the cosmic microwave background, were emitted when the matter at that location was much closer to us, because the universe was much smaller then. At the moment of decoupling, the physical temperature of the cosmic microwave background photons was about 3000 Kelvin. This is in the infrared part of the electromagnetic spectrum, similar to the heat you feel from a glowing ember or a piece of metal hot enough to glow dull red. If you could have existed at that moment, if you could have seen with infrared sensitive eyes, the entire universe would have glowed with a deep red light coming from all directions at once, filling space with the light of creation. But you would have had to act quickly if you wanted to see that glow, because it was rapidly fading and cooling as the universe expanded. Remember, the expansion of space stretches the wavelengths of photons traveling through it. This stretching is called cosmological redshift, and it's one of the most fundamental features of an expanding universe. As space doubles in size, wavelengths double too. A photon that started out in the infrared gets stretched into the microwave, a microwave photon gets stretched into the radio wave region, the wavelength increases in direct proportion to the size of the universe. Since the moment of decoupling, the universe has expanded by a factor of about 1090. This factor is often written as 1 plus z, where z is the redshift. So we say the cosmic microwave background comes from a redshift of z equals 1089. The universe is now 1090 times larger than it was at decoupling, which means the wavelengths of the CMB photons are now 1090 times longer, and correspondingly, the temperature is 1090 times cooler. 3000 Kelvin divided by 1090 gives us about 2.7 Kelvin. That's the temperature of the cosmic microwave background today. Those infrared photons from the glowing plasma at recombination have been stretched by the expansion of the universe into microwave photons, cooled to just barely above absolute zero, but still carrying the imprint of their origin, still preserving the pattern of temperature and density variations from that ancient epoch. Here's something beautiful to contemplate. The photons that left the surface of last scattering have been traveling toward us for over 13 billion years. They've crossed an unimaginable distance, witnessed the formation of the first stars, watched galaxies assemble and cluster, pass through vast voids and dense clouds of gas, all while the universe expanded around them, stretching their wavelengths, cooling their energy, but never stopping their forward motion through space. And now, today, this very moment as you listen to these words, those photons are arriving at Earth. Some of them are striking radio telescopes and being detected. Some are passing through your body. Some will continue on, traveling past Earth and continuing their journey through the cosmos. They've been traveling since before the sun existed, since before the Milky Way had its current shape, since before most of the stars in the universe had formed. They are messengers from the dawn of time, and they bring with them information about the universe in its infancy, information we can decode and study and use to understand our cosmic origins. But the cosmic microwave background didn't reveal all its secrets when Penzias and Wilson first detected it. That initial discovery confirmed that the radiation existed and that it had the right temperature to be the remnant of the Big Bang. But the real scientific revolution came later, when astronomers developed instruments sensitive enough to detect the tiny temperature variations across the sky, to map the structure of the infant universe, to see the seeds of galaxies frozen into the ancient light. The cosmic cartographers. For nearly 2 decades after Penzias and Wilson's discovery, astronomers knew the cosmic microwave background existed, but they couldn't map its structure in detail. Ground-based and balloon-borne experiments made measurements, but the Earth's atmosphere interferes with microwave observations, absorbing and emitting at these wavelengths, adding noise and contamination to the signal. What was needed was a satellite, an instrument that could observe from above the atmosphere, that could scan the entire sky with high sensitivity and precision, that could measure temperature variations of millionths of a degree. That satellite was COBE, the Cosmic Background Explorer, launched by NASA on November 18, 1989. COBE was not a sleek, streamlined spacecraft. It looked functional rather than elegant, a collection of instruments and detectors packed together with the liquid helium needed to cool them to the extraordinarily low temperatures required for sensitive infrared and microwave detection. but it was revolutionary in its capabilities. COBE carried three main instruments. One was called FIRAS, the Far Infrared Absolute Spectrophotometer, designed to measure the spectrum of the cosmic microwave background with unprecedented precision. The second was DIRBE, the Diffuse Infrared Background Experiment, intended to map infrared light from our own galaxy and from distant sources. And the third was DMR, the Differential Microwave Radiometers, which would search for the tiny temperature variations in the CMB that theorists predicted must be there if galaxies were to have formed from gravitational collapse. The first major result came from FIRAS. When the team analyzed their data and plotted the spectrum of the cosmic microwave background, they found something almost unbelievable. The CMB followed a black-body curve so perfectly that the data points and the theoretical prediction were indistinguishable. The spectrum was perfect to within the measurement error, which was extraordinarily small. This was the most precise confirmation yet that the universe had once been in thermal equilibrium, that matter and radiation had been intimately coupled, exactly as the Big Bang theory predicted. But the result that truly shook the scientific community came from the DMR instrument. In April of 1992, at a meeting of the American Physical Society in Washington, D.C., the COBE team announced that they had detected temperature variations in the cosmic microwave background. The variations were tiny, only about 1 part in 100,000, fluctuations of about 30 millionths of a degree, but they were definitely there, spread across the sky in a pattern that looked random and mottled, like the surface of a pond disturbed by countless raindrops. The news made the front page of the New York Times the next day. Stephen Hawking called it the discovery of the century, if not of all time. George Smoot, one of the principal investigators on COBE, said it was like seeing God, a phrase that would become famous and controversial in equal measure. But the religious language captured something important about the moment. For the first time, humanity could see the structure of the universe as it was in its infancy, could observe the patterns imprinted by whatever process created the initial density variations, could trace the lineage of every galaxy and star back to these tiny fluctuations in the primordial plasma. The pattern COBE detected was consistent with what theorists had predicted. The fluctuations had the right amplitude, the right statistical properties, the right distribution across different angular scales. They were the seeds of cosmic structure preserved in the cosmic microwave background, waiting to be discovered. Over billions of years, these tiny density variations would grow under the influence of gravity. The denser regions would attract more matter, becoming denser still. The less dense regions would lose matter to their denser neighbors, becoming voids. Eventually, the dense regions would fragment and collapse to form the first stars, then galaxies, then the vast cosmic web of structure we observe today. For this discovery, John Mather and George Smoot were awarded the Nobel Prize in Physics in 2006. The Nobel Committee noted that COBE's measurements had provided strong support for the Big Bang theory and had enabled cosmology to become a precision science. But COBE was only the beginning. Its measurements were groundbreaking, but they had limitations. The angular resolution of the DMR instrument was about 7 degrees, which meant that features smaller than 7 degrees on the sky couldn't be resolved. To push deeper, to see finer details in the cosmic microwave background, a new mission would be needed. That mission was WMAP, the Wilkinson Microwave Anisotropy Probe, launched by NASA on June 30th, 2001. WMAP was named in honor of David Wilkinson, a cosmologist at Princeton who had been part of the team searching for the CMB in the 1960s and who had contributed to WMAP's development before his death in 2002. WMAP was designed specifically to map the temperature variations in the cosmic microwave background with much higher resolution and sensitivity than COBE. While COBE had an angular resolution of about 7 degrees, WMAP could resolve features as small as about 1/3 of a degree, more than 20 times finer detail. WMAP orbited at a special location called the second Lagrange point, about 1.5 million kilometers from Earth in the direction away from the Sun. From this vantage point, the Earth, Moon, and Sun all lie in roughly the same direction, making it easier to shield the sensitive detectors from their radiation. WMAP operated for 9 years, far longer than its original 2-year mission, scanning the sky repeatedly and building up exquisitely detailed maps of the cosmic microwave background temperature variations. The results from WMAP were extraordinary. The maps showed intricate structure, a complex pattern of hot and cold spots distributed across the entire sky. The hot spots, colored red in the typical false color images, were regions where the CMB was slightly warmer, corresponding to slightly denser regions in the primordial plasma. The cold spots, colored blue, were slightly cooler and less dense. The variations were still incredibly small, only about 200 millionths of a degree, but WMAP could measure them with high precision. From these maps, cosmologists could extract a wealth of information. By analyzing the statistical properties of the temperature fluctuations, by looking at how the power in the variations was distributed across different angular scales, they could measure fundamental properties of the universe, the age of the universe, the density of ordinary matter, dark matter, and dark energy, the geometry of space, the rate of expansion, parameters that had been uncertain by factors of 2 or more suddenly became known to percent-level precision or better. WMAP confirmed that the universe is 13.8 billion years old, give or take 1%. It showed that the universe is geometrically flat or very close to it, meaning that parallel lines remain parallel and the angles of triangles add up to 180 degrees even over cosmic distances. It measured the composition of the universe, about 5% ordinary matter, the atoms that make up stars and planets and people, about 20% dark matter, the mysterious stuff that makes up most of the universe, and about 70% dark energy, the mysterious stuff that makes up most of the universe, 7% dark matter, an unknown substance that interacts only through gravity, and about 68% dark energy, an even more mysterious component causing the expansion of the universe to accelerate. These measurements transformed cosmology. Before WMAP, cosmologists had competing models and significant uncertainties. After WMAP, there was a standard model of cosmology, a framework that described the universe's history from a fraction of a second after the Big Bang to the present day, tested against multiple independent lines of evidence and confirmed to high precision. The cosmic microwave background had become the cornerstone of this standard model, the single most important source of information about the universe's initial conditions and large-scale properties. But even WMAP wasn't the final word. In May of 2009, the European Space Agency launched Planck, a satellite designed to map the cosmic microwave background with even higher resolution and sensitivity than WMAP. Planck operated at 9 different frequencies, allowing it to better separate the CMB signal from contaminating foreground emissions from our own galaxy. Its angular resolution was better than 1/10 of a degree, more than 3 times finer than WMAP. Its sensitivity was extraordinary, able to detect temperature variations of just a few millionths of a degree. Planck operated for 4 years, completing 5 full sky surveys before running out of coolant for its most sensitive detectors. When the Planck team released their final results, they presented the most detailed map of the cosmic microwave background ever made, an all-sky image showing structures down to the finest scales observable, with exquisite precision and minimal contamination from other sources. The map is beautiful, a modeled pattern of red and blue and everything in between, each color representing a tiny temperature variation, each variation corresponding to a density fluctuation in the universe when it was just 380,000 years old. Looking at that map, you're seeing the universe in its infancy. You're seeing the raw material that would eventually become galaxies and stars. You're seeing patterns imprinted by processes that occurred in the first fraction of a second after the Big Bang, perhaps even signatures of cosmic inflation, a period of extraordinarily rapid expansion that may have occurred when the universe was less than 1/trillionth of a trillionth of a trillionth of a second old. Every feature in that map tells a story. Every hot spot and cold spot, every variation in color and intensity carries information about the fundamental nature of reality, the forces and particles and fields that govern the universe's behavior. And we've learned to read that map. We've developed sophisticated mathematical techniques to extract information from the temperature variations, to compare them with theoretical predictions, to test different models of what might have happened in the early universe. The cosmic microwave background has become a laboratory for fundamental physics, a window into conditions and energies that could never be replicated on Earth, a cosmological Rosetta Stone that helps us decode the language of creation itself. But what exactly are we reading when we analyze the cosmic microwave background? What do those patterns mean? To understand that, we need to explore the physics of the primordial plasma, the forces and processes that created the temperature variations we observe today. Written in light. When you look at a map of the cosmic microwave background, at first glance it might seem random, like noise, like the static that used to appear on old television screens. But it's not random. Hidden in that seemingly chaotic pattern is an extraordinary amount of structure and information, patterns that emerge from the physics of sound waves in the primordial plasma, frozen into place at the moment of recombination and preserved for billions of years in the ancient light. Imagine the universe in its first moments after the Big Bang. At this epoch, on the largest scales, the universe is remarkably uniform. The temperature and density are nearly the same everywhere, but there are tiny variations, small regions that are slightly denser or slightly less dense than average. The origin of these variations is still a matter of active research, but the leading theory is that they arose from quantum fluctuations during cosmic inflation, random variations in the quantum fields that filled the universe, amplified to cosmic scales by the exponential expansion of space. These density variations have consequences. Where there's slightly more matter than average, there's slightly more gravity. This extra gravity tries to pull more matter in, trying to make the dense region denser. But in the early universe, the situation is more complex than simple gravitational collapse, because matter and radiation are coupled together into a unified fluid. The photons provide enormous pressure that resists compression. When gravity tries to squeeze matter into the overdense regions, the photons push back, creating outward pressure that opposes the inward pull of gravity. This creates an oscillation, a wave, quite literally a sound wave propagating through the photon baryon fluid. The dense region compresses under gravity, heating up as it compresses, increasing the radiation pressure. Eventually, the pressure becomes strong enough to halt the compression and reverse it. The region expands, cools, and the pressure decreases. Gravity takes over again and pulls it back inward. The region oscillates, alternately compressing and expanding, exactly like a sound wave in air, but happening in the plasma of the early universe. These are called Baryon acoustic oscillations, or BAO, named for the baryons, the protons and neutrons that make up ordinary matter that oscillate along with the photons. The sound waves propagate outward from every density perturbation at a specific speed determined by the properties of the photon baryon fluid. The speed turns out to be about 1/3 the speed of light, enormously fast by everyday standards, but slow enough that the waves don't travel infinitely far before recombination occurs. Think about what's happening here in more detail. Each initial overdensity acts like the impact point of a pebble dropped into a pond. Waves spread outward in all directions. But unlike water waves, which are two-dimensional ripples on a surface, these are three-dimensional waves propagating through the volume of space. They create spherical shells of slightly enhanced density expanding away from the initial perturbation. At the moment of recombination, when the universe becomes transparent, these shells are frozen in place. The material at the shell radius, roughly 450,000 light years from the original perturbation, has been compressed by the sound wave and is slightly denser than the surrounding regions. Now imagine this happening not just at one location, but everywhere simultaneously. The early universe had perturbations at every point, each generating its own expanding shell of enhanced density. These shells overlap and interfere with each other in complex ways, creating a rich pattern of density variations across space. But despite this complexity, there's a characteristic scale imprinted in the pattern, the scale of the sound horizon, the maximum distance sound could have traveled before recombination. The distance these sound waves can travel before recombination is called the sound horizon. It's determined by how long the waves can propagate from the earliest moments when the perturbations formed until the moment of recombination when the oscillations freeze, and by the speed at which they travel. The physics that determines the sound horizon is well understood. We know the temperature of the universe as a function of time. We know the composition of the primordial plasma. We know how fast sound waves travel in that plasma. We can calculate the sound horizon with high precision. At the moment of recombination, The sound horizon corresponds to about 450,000 light years, or about 140,000 parsecs. That's the farthest distance that sound waves in the photon baryon fluid could have traveled from any given point before recombination froze them in place. In today's universe, after more than 13 billion years of cosmic expansion, that distance has been stretched to about 490 million light years, or about 150 megaparsecs. This length scale is imprinted in the distribution of matter and appears as a characteristic size in the patterns we observe in the cosmic microwave background. When we analyze the temperature variations in the CMB, we don't just look at the raw map of hot and cold spots. We perform a mathematical decomposition, breaking down the pattern into components at different angular scales. Imagine taking the CMB map and asking, how much of the variation occurs on very large scales, features spanning many degrees on the sky? How much occurs on intermediate scales, features a few degrees across? How much on small scales, features of an arc-minute or less? This decomposition is similar to how you might analyze a musical chord by identifying all the individual notes within it, or how you might analyze a complex sound by identifying all the different frequencies it contains. The result of this decomposition is called the angular power spectrum of the cosmic microwave background. It's a graph showing how much temperature variation exists at each angular scale, from the largest features spanning the entire sky down to the smallest features the telescope can resolve. And when you plot this power spectrum, something remarkable appears. It's not smooth. It's not a simple curve decreasing monotonically from large scales to small. Instead, it has peaks and valleys, oscillations in the power at different angular scales, a pattern that looks almost like a wave itself. These peaks in the power spectrum are the signature of Baryon acoustic oscillations. Each peak corresponds to a particular mode of oscillation in the primordial plasma. The first peak, the largest and most prominent, occurs at an angular scale of about 1 degree. This corresponds to sound waves that compressed exactly once between their formation and recombination. Regions that were in the compression phase of their first oscillation when the universe became transparent. The second peak corresponds to regions that had time to compress, expand, and compress again, completing one full oscillation and entering their second compression. The third peak corresponds to regions that completed 1.5 oscillations, and so on. The heights and positions of these peaks tell us about the universe's composition and geometry. The location of the first peak is particularly sensitive to the curvature of space. If the universe were closed, curving back on itself like the surface of a sphere, angles would appear larger, and the first peak would shift to larger angular scales. If the universe were open, curving like a saddle, angles would appear smaller and the peak would shift to smaller scales. The observed location of the first peak tells us the universe is flat or extremely close to it, with space geometry described by Euclidean geometry on large scales. The relative heights of the peaks tell us about the density of ordinary matter. More baryons means stronger gravitational compression, which enhances the odd-numbered peaks relative to the even-numbered ones. The detailed shape and height of the peaks also depends on the density of dark matter, which contributes to the gravitational potential, but doesn't couple to the photons and thus affects the oscillations differently than ordinary matter. By fitting theoretical models to the observed power spectrum, cosmologists can measure the densities of both ordinary and dark matter with remarkable precision. There are other features in the power spectrum as well. At very small angular scales, the power drops off more steeply than it would if the plasma were perfectly ideal. This damping occurs because the photons can diffuse slightly through the plasma, smoothing out variations on the smallest scales. The amount of damping depends on the properties of the plasma, including its temperature and density, and measuring it provides another independent constraint on the universe's composition. All of this information, the peaks, the damping, the overall shape of the power spectrum, comes from the pattern of temperature variations in the cosmic microwave background. It's encoded in the ancient light, written in the language of physics, waiting for us to decode it, and we have decoded it with extraordinary success. The theoretical predictions match the observations so precisely that there's no doubt we understand the basic physics of the early universe, the processes that created these patterns, the evolution from the smooth initial state to the rich structure we see today. But the cosmic microwave background has even more to tell us. Beyond the temperature variations, there's additional information encoded in the polarization of the light, in the way the electromagnetic waves oscillate as they travel through space. This polarization carries its own signatures, its own stories about the early universe, and unlocking these stories has been one of the frontiers of modern cosmology. Beyond temperature, light is a wave, an oscillation in the electromagnetic field that propagates through space at the speed of light. The oscillation has a direction called the polarization direction, which indicates how the electric and magnetic fields are oriented perpendicular to the direction the light is traveling. Natural sunlight or starlight is usually unpolarized, with the electromagnetic waves oscillating in random directions. But under certain conditions, light can become polarized, with a preferred direction of oscillation. The cosmic microwave background is slightly polarized. Not all of it, and not by a large amount, but about 10% of the CMB radiation has a preferred polarization direction. This polarization is created at the moment of last scattering through a process called Thomson scattering, the same interaction between photons and electrons that kept the universe opaque before recombination. Here's how it works. Imagine an electron sitting in the primordial plasma, surrounded by photons coming from all directions. If the radiation field were perfectly uniform, with exactly the same intensity of light coming from every direction, the electron wouldn't experience any net force, and the light it scattered would remain unpolarized. But if the radiation field has a quadrupole pattern, with more light coming from some directions than others, specifically with a pattern that varies at 90-degree intervals, then the scattering process can create polarized light. Let me explain this a bit more carefully, because it's subtle but important. When unpolarized light scatters off an electron, the polarization of the scattered light depends on the geometry of the scattering. Light that scatters at a 90-degree angle becomes polarized perpendicular to the plane of scattering. If there's more light coming from one direction than another, this preferential scattering creates a net polarization in the scattered radiation. The quadrupole pattern is special because it has exactly the right symmetry to produce linear polarization through Thomson scattering. This quadrupole pattern exists in the CMB because of the density variations we've been discussing, Where there's an overdensity, there's slightly more radiation. Where there's an underdensity, there's slightly less. These variations create temperature differences, and temperature differences create intensity differences, and intensity differences with the right geometry can create polarization when scattered by electrons. The polarization pattern that results carries information about the distribution of matter at the last scattering surface, providing a complementary view of the same physics that creates the temperature variations. But there's more. The polarization of the cosmic microwave background comes in two types, which physicists call E modes and B modes, named by analogy with the electric and magnetic fields in electromagnetism. E modes have a polarization pattern that can be created by density perturbations, the kind we've been discussing. They were detected by WMAP and have been measured extensively by Planck and other experiments. E-mode polarization confirms our understanding of the last scattering surface and provides additional constraints on cosmological parameters. B-modes are different. B-modes have a swirling, rotational pattern that cannot be created by density perturbations alone. They require something to twist space itself to create gravitational effects that can imprint this distinctive pattern. One possible source is gravitational lensing. As CMB photons travel from the last scattering surface to us, they pass through regions of space where matter creates gravitational fields. These fields bend the path of the photons very slightly, distorting the pattern of temperature and polarization. This gravitational lensing converts some E modes into B modes, creating a weak B mode signal that has been detected by several experiments. But there's another potential source of B modes, one that would be far more significant if detected. During cosmic inflation, the incredibly rapid expansion that may have occurred in the first fraction of a second after the Big Bang, space itself would have been stretched and squeezed by passing gravitational waves. These primordial gravitational waves would have left an imprint on the cosmic microwave background, creating a B-mode polarization signal that could be detected today. Finding this primordial B-mode signal would be direct evidence for inflation, confirming that the universe underwent this period of exponential expansion and would provide information about the energy scale at which inflation occurred. The search for primordial B-modes has become one of the most active areas of observational cosmology. Multiple experiments from ground-based telescopes in Antarctica and Chile to balloon-borne instruments to proposed space missions are designed to measure the polarization of the cosmic microwave background with exquisite sensitivity, hoping to detect the faint swirl of polarization that would signal the presence of primordial gravitational waves. So far, only the lensing B modes have been definitively detected. The primordial signal, if it exists at the predicted level, remains elusive, hiding at the edge of detectability, waiting for the next generation of instruments to reveal it. Beyond polarization, there are other ways the cosmic microwave background carries information about the universe. As the CMB photons travel from the last scattering surface to us, they pass through the evolving universe, through regions where galaxies are forming, where clusters are assembling, where large-scale structure is developing. Along the way, they can interact with this structure, gaining or losing energy, changing direction, acquiring subtle modifications to their original temperature and polarization pattern. One such interaction is called the Sunyaev-Zeldovich effect, named after the Soviet physicists who predicted it in the 1960s. When CMB photons pass through a cluster of galaxies, they can scatter off the hot electrons in the gas that fills the cluster. These electrons are moving at high speeds, and when they scatter the CMB photons, they transfer some of their energy to the photons through a process called inverse Compton scattering. The CMB photons gain energy, shifting to slightly higher frequencies, creating a distortion in the blackbody spectrum when viewed in the direction of the cluster. The Sunyaev-Zeldovich effect is remarkable because its strength doesn't depend on the distance to the galaxy cluster, unlike optical light, which gets fainter with distance following the inverse square law. The change in the CMB caused by the Sunyaev-Zeldovich effect is determined only by the properties of the cluster itself, not by how far away it is. This makes it a powerful tool for finding galaxy clusters at high redshifts where they're too faint or too distant to detect easily with optical telescopes. Surveys using the Sunyaev-Zeldovich effect have discovered thousands of galaxy clusters, tracing the growth of structure across cosmic history. Another effect is gravitational lensing, which we mentioned briefly in the context of B-mode polarization. The mass in the universe creates gravitational fields that curve space, and these curvatures deflect the paths of photons traveling through them. The cosmic microwave background is no exception. As CMB photons travel toward us, their paths are bent by the gravitational fields of galaxies, clusters, and large-scale structure. This bending causes the temperature and polarization patterns we observe to be slightly distorted compared to what they were at the last scattering surface. By measuring this distortion carefully, cosmologists can reconstruct the distribution of matter along the line of sight, creating maps of the gravitational potential through which the CMB photons traveled. These lensing maps provide yet another probe of the universe's structure, independent of direct observations of galaxies and complementary to the information in the CMB temperature fluctuations themselves. The combination of all these different probes, temperature, polarization, lensing, secondary effects, makes the cosmic microwave background an extraordinarily rich source of information about the universe. Every new measurement, every improvement in sensitivity and resolution reveals more detail, more structure, more subtle effects that can be compared with theoretical predictions and used to test our understanding of cosmology. The cosmic microwave background has evolved from a simple detection of a uniform glow to a detailed, multifaceted portrait of the universe, and that portrait continues to sharpen with each new generation of instruments. Beyond the expanding canvas. There's something deeply poetic about the cosmic microwave background's history. The light we detect today was created at a specific moment, 380,000 years after the Big Bang, but it hasn't remained static since then. It's been traveling, evolving, changing as the universe around it expanded. To understand the CMB fully, we need to understand this evolution, this long journey from the moment of creation to the present day. At the instant of last scattering, when electrons and protons combined to form neutral hydrogen and the universe became transparent, the photons that would become the cosmic microwave background had a temperature of about 3,000 Kelvin. At this temperature, the peak wavelength of the radiation, according to Wien's displacement law, is about 1,000 nanometers, or 1 micron, in the near-infrared part of the spectrum. If you could see infrared light, the universe at this moment would glow orange-red, like hot metal in a forge, surrounding you completely with light coming from every direction. But the universe is expanding. Space itself is growing larger, stretching, and as it stretches, it carries the photons along with it. This stretching affects the wavelength of the light. A photon with a wavelength of 1 micron traveling through expanding space will have its wavelength increased in direct proportion to the expansion. If the universe doubles in size, the wavelength doubles. If the universe expands by a factor of 1,000, the wavelength increases by a factor of 1,000. Since the epoch of last scattering, the universe has expanded by a factor of approximately 1,090. We know this from the redshift of the cosmic microwave background, which is measured to be about 1,089. The redshift is defined as the fractional change in wavelength. If a photon's wavelength has increased by a factor of 1,090, its redshift is 1,089. This enormous expansion factor means that those infrared photons with wavelengths of 1 micron have been stretched to wavelengths of about 1 millimeter, right in the heart of the microwave region of the spectrum. This stretching also affects the energy of the photons. The energy of a photon is inversely proportional to its wavelength. Shorter wavelengths mean higher energy. Longer wavelengths mean lower energy. As the wavelength increases by a factor of 1,090, the energy decreases by the same factor. Correspondingly, the temperature decreases. The 3,000 Kelvin plasma at recombination has cooled to 2.7 Kelvin radiation today, simply through the expansion of space. This cooling is universal and continuous. Every moment as space expands, the cosmic microwave background gets slightly cooler, its wavelengths slightly longer, its photons slightly less energetic. The rate of cooling depends on the expansion rate of the universe, which in turn depends on the total energy density, including matter, dark energy, and the radiation itself. In the current universe, dark energy dominates, causing the expansion to accelerate, but the basic principle remains. Expansion means cooling, and the CMB is gradually fading, slowly declining toward the ultimate cold of an infinitely expanded universe. Think about what this means for the future. As billions of years pass, the cosmic microwave background will continue to cool. In another 1 trillion years, if the universe continues expanding as current models predict, the CMB will have cooled to a fraction of a degree above absolute zero. In 10 trillion years, it will be even colder. Eventually, in the unimaginably distant future, the CMB will become so cold, its photons so low in energy, that detecting it will become effectively impossible even with perfect instruments. The evidence for the Big Bang, written in this ancient light, will fade from the universe. Future civilizations, if any exist, will have to rely on theory and indirect evidence rather than direct observation. But we don't live in that distant future. We live now in an epoch when the CMB is still readily detectable, when its temperature is high enough and its photons energetic enough that we can map it with current technology. We are fortunate in our timing. This evolution of the cosmic microwave background is one of the most powerful pieces of evidence for the Big Bang model. If the universe were static, unchanging, the CMB would have no explanation. Where would this uniform radiation come from? Why would it have a black body spectrum? Why would it be present everywhere at the same temperature? But in an expanding universe that was once hot and dense, the CMB is a natural consequence, a remnant of that early hot state, cooled by expansion, stretched to longer wavelengths, but still present, still detectable, still carrying information about its origin. Alternative theories such as the steady-state model, popular in the mid-20th century, could not explain the cosmic microwave background. The steady-state model proposed that the universe had no beginning and no end, that it maintained a constant average density despite expansion by continuously creating new matter. This model could explain the expansion of the universe and the recession of galaxies, but it had no mechanism to create a uniform bath of microwave radiation with a perfect black-body spectrum. When Penzias and Wilson discovered the CMB, it was a death blow to the steady-state model. Within a few years, most cosmologists had abandoned it in favor of the Big Bang. The detection of the cosmic microwave background, combined with the observation that the universe is expanding, with measurements of the abundances of light elements created in Big Bang nucleosynthesis, and with studies of the large-scale structure of the universe, forms a web of interlocking evidence that all points to the same conclusion. The universe had a beginning. It was once extremely hot and dense, and it has been expanding and cooling for nearly 14 billion years. Each piece of evidence supports and reinforces the others. Each new observation confirms the basic framework and refines our understanding of the details. And the details matter. The cosmic microwave background isn't just evidence that the Big Bang occurred. It's a detailed record of the conditions in the early universe, a snapshot that allows us to measure fundamental parameters with remarkable precision. Before the CMB was mapped in detail, cosmologists had to estimate the age of the universe from indirect evidence with uncertainties of billions of years. Now we know the age to better than 1% precision, 13.8 billion years. Before the CMB, the composition of the universe was highly uncertain. Now we know that ordinary matter makes up about 5%, dark matter about 27%, and dark energy about 68%, with errors of only a few percent. These measurements have transformed cosmology from a field where different researchers could have wildly different ideas about fundamental questions. How old is the universe? What is it made of? What is its geometry? To a field where there's broad consensus on the basic framework, and the research focuses on refining measurements and exploring open questions within that framework. The cosmic microwave background is the foundation of this transformation, the observational pillar on which modern cosmology rests. The universe in numbers. Numbers can sometimes feel cold and abstract, disconnected from the beauty and wonder of the cosmos. But the numbers we've extracted from the cosmic microwave background tell a story, and it's worth taking a moment to appreciate what that story reveals about the universe we inhabit. 13.8 billion years. That's the age of the universe according to measurements of the cosmic microwave background, combined with our understanding of how the universe has expanded since the moment of last scattering. Think about that span of time for a moment. If you could somehow compress the entire history of the universe into a single year, with the Big Bang occurring at midnight on January 1st. The CMB would be emitted on January 2nd. The first stars would form around January 12th. The Milky Way would begin to assemble in mid-January. Our solar system wouldn't form until September. Complex life on Earth wouldn't emerge until late November. All of recorded human history, every empire and civilization, every discovery and invention would occur in the last minute of December 31st. The universe is incomprehensibly old by human standards, and yet the cosmic microwave background takes us back to when it was less than 400,000 years old, practically to the moment of creation in cosmological terms. We're seeing the universe as an infant before it had even begun to form the structures that would eventually become galaxies and stars. This is remarkable when you reflect on it. We're not looking at the universe as it was a few billion years ago, or even a few 100 million years ago. We're looking at it when it was less than 1/30,000th its current age. That's like seeing a photograph of a 70-year-old person taken in the first hours after their birth. 5% ordinary matter, that's one of the most surprising results from CMB measurements. When you look around, you see matter everywhere. Planets, stars, gas clouds, galaxies, all made of protons, neutrons, and electrons, the ordinary matter of everyday experience. But all of that, all the matter we can see and touch and build things from, represents only about 5% of the total energy content of the universe. It's a small minority, a trace constituent in the cosmic recipe, 27% dark matter. This is something else entirely. We don't know what dark matter is made of. It's not made of protons and neutrons. It's not made of electrons. It doesn't emit light or absorb light or interact with electromagnetic radiation in any way we've been able to detect. We know it exists because of its gravitational effects. Galaxies rotate too fast for the matter we can see to hold them together. Clusters of galaxies have too much gravity for the visible matter to account for. The cosmic microwave background has patterns that require dark matter to have existed in the early universe, contributing to the gravitational potential that drove the oscillations we observe. Dark matter is invisible but essential. Without it, galaxies wouldn't have formed when they did. The density of ordinary matter alone isn't enough to create the gravitational wells needed to assemble the first stars in the time available. Dark matter provides the gravitational scaffolding, the framework onto which ordinary matter falls, condensing and cooling and eventually forming stars and planets. We wouldn't exist without dark matter, and yet we still don't know what it is. It remains one of the great mysteries of modern physics. 68% dark energy. This is perhaps the most mysterious component of all. Dark energy is whatever is causing the expansion of the universe to accelerate. When astronomers studied distant supernovae in the late 1990s, they discovered that the universe isn't just expanding. It's expanding faster and faster. Something is pushing space apart, overcoming the attractive force of gravity that should be slowing the expansion. We call that something dark energy, but the name is more a label for our ignorance than a description of what it actually is. The cosmic microwave background provides independent evidence for dark energy and helps constrain its properties. The patterns in the CMB depend on the geometry of space, which in turn depends on the total energy density of the universe. The observed pattern is consistent with a flat universe, which requires the total energy density to be at a critical value. The measured amounts of ordinary matter and dark matter fall short of this critical value. Something else is needed to make the universe flat, and that something is dark energy, contributing about 68% of the total. Dark energy behaves very differently from ordinary matter or dark matter. Matter clumps together under gravity, forming structures. Dark energy doesn't clump. It remains uniformly distributed, filling space homogeneously, and its density doesn't decrease as the universe expands. In fact, if dark energy behaves like a cosmological constant, as observations suggest, its density remains exactly constant even as space grows larger. This means that as the universe expands, the amount of dark energy per cubic meter stays the same, which means the total amount of dark energy is increasing, growing in direct proportion to the volume of space. This has profound implications for the future. As the universe continues to expand, dark energy will become increasingly dominant. The galaxies we can see today will be carried farther and farther away by the accelerating expansion. Eventually, distant galaxies will recede faster than light can travel through expanding space, disappearing beyond what's called the cosmic horizon. In the far future, trillions of years from now, an observer in the Milky Way would see a universe that appears almost empty, with only the handful of galaxies in the local gravitationally bound group still visible. The cosmic microwave background itself will cool to temperatures so low that it will be effectively undetectable. The universe will become a lonely, dark place, but that's far in the future. For now, we live in an epoch where the CMB is detectable, where we can measure it and learn from it, where the ancient light still carries clear signatures of the universe's youth. We're fortunate to exist at a time when cosmology is possible, when the evidence for the universe's history is still accessible to observation and measurement. The geometry of the universe is flat or very nearly so. This is another crucial finding from CMB measurements. The first peak in the angular power spectrum occurs at an angular scale that depends on the curvature of space. If space were curved like the surface of a sphere, parallel light rays would eventually converge, and angular sizes would be distorted in a predictable way. If space were curved like a saddle, parallel rays would diverge. The observed position of the first peak indicates that space is flat to within about half of 1%. Parallel lines remain parallel. Triangles have angles that sum to 180 degrees. The universe obeys Euclidean geometry on large scales. This flatness is puzzling in some ways. In the early universe, any deviation from perfect flatness would have been amplified by the expansion. A universe that started out even slightly curved would have become dramatically curved by now, either collapsing back on itself or expanding so rapidly that no structure could form. The fact that the universe is flat today suggests it was extraordinarily close to flat in the beginning, which seems like a remarkable coincidence unless there's some mechanism to explain it. That mechanism may be cosmic inflation. During the inflationary epoch, The universe expanded so rapidly that any initial curvature was stretched flat, just as the surface of a balloon becomes flatter as you inflate it larger and larger. Inflation naturally produces a flat universe, and the flatness we observe is consistent with the predictions of inflationary models. The cosmic microwave background, by measuring the geometry so precisely, provides strong support for inflation, though not yet definitive proof. All of these numbers, these percentages and ages and compositions come from the pattern of light in the cosmic microwave background. They're extracted through careful analysis, comparing theoretical models with observations, adjusting parameters to find the best fit. The precision is remarkable, but it's not perfect. There are still uncertainties, still open questions, still aspects of the CMB that we don't fully understand. Our place in this light. As we near the end of this journey through the cosmic microwave background, I want to step back from the numbers and the physics, the satellites and the power spectra, and reflect on what this all means, not in a scientific sense, but in a human sense. What does it mean that we can detect this ancient light? What does it tell us about our place in the universe, our connection to the cosmos, the nature of existence itself? The cosmic microwave background is a boundary. It represents the farthest back in time we can see using light. Before the moment of recombination, the universe was opaque. Photons couldn't travel freely. Information about earlier times is not carried by the CMB, at least not in a direct way. We can infer what happened earlier through theoretical models, through the patterns imprinted on the CMB, but we cannot see it directly. The surface of last scattering is a kind of cosmic horizon beyond which our view is blocked, a barrier we cannot penetrate with electromagnetic radiation. This boundary is humbling. For all our telescopes and all our instruments, for all our mathematical sophistication and theoretical understanding, we are limited. We cannot see the first moments after the Big Bang. We cannot observe the birth of time and space. We are constrained by the physics of the universe itself, by the fundamental fact that information cannot travel faster than light, and that light could not travel freely in the opaque early universe. And yet, 380,000 years after the Big Bang is remarkably early. In cosmic terms, it's practically the beginning. The universe has existed for 13.8 billion years, and we can see it when it was less than 400,000 years old. That's seeing it at less than 0.03% of 1% of its current age. It would be like observing a 70-year-old person as they appeared 3 hours after birth. The cosmic microwave background gives us an incredibly early glimpse of the universe, even if we cannot see all the way back to the absolute beginning. There's also something profound about the connection between us and this ancient light. The atoms that make up your body were not present at the moment of last scattering. At that time, the universe contained only hydrogen, helium, and trace amounts of lithium. The heavier elements, carbon, nitrogen, oxygen, iron, everything that makes up living things and rocky planets, were created later in the cores of stars through nuclear fusion and in supernova explosions that scattered those elements through space. But the hydrogen in your body, the single protons that form the nuclei of hydrogen atoms, those did exist at recombination. They were there, part of the primordial plasma, participating in the Baryon acoustic oscillations, contributing to the density fluctuations that would eventually collapse to form galaxies. In a very real sense, you are made of material that was present at the moment the cosmic microwave background was created. You are cosmically connected to that ancient epoch. Consider this more deeply for a moment. The protons in your body are approximately 13.8 billion years old. They were formed in the first few minutes after the Big Bang, during the epoch of Big Bang nucleosynthesis, when the universe was hot and dense enough for nuclear reactions to occur. These same protons then spent hundreds of thousands of years bouncing around in the primordial plasma, constantly interacting with photons and electrons, participating in the cosmic dance of matter and radiation. When recombination occurred and the universe became transparent, those protons found their electrons and became neutral hydrogen atoms, settling into the gas clouds that would eventually collapse to form stars and galaxies. More than that, you are made of atoms that were forged in stars, stars that formed from gas clouds that collapsed under gravity, gas clouds that grew from tiny density variations in the primordial universe, variations we can see in the cosmic microwave background. The patterns in the CMB are the ancestors of the galaxies, which are the ancestors of the stars, which are the ancestors of the elements, which are the ancestors of you. There's an unbroken chain of causation connecting the fluctuations in the ancient light to your existence right now. Listening to these words, this is not poetry, it's physics. It's the literal history of the universe, traced through billions of years of cosmic evolution. You exist because the early universe had density fluctuations. If the CMB were perfectly uniform, if there were no temperature variations, no acoustic oscillations, no seeds for structure formation, there would be no galaxies, no stars, no planets, no life. The tiny imperfections in the primordial plasma, those 1 part in 100,000 variations in temperature, were essential for your existence. The cosmic microwave background also reminds us of the universe's immensity and our smallness within it. The light we detect has traveled for over 13 billion years to reach us. It has crossed distances so vast that they're difficult to comprehend. The sphere of last scattering surrounding us has a radius of about 46 billion light years in today's coordinates, accounting for the expansion of space. That means the matter that emitted the CMB photons we see today is now roughly 46 billion light years away, carried to that distance by the expansion of the universe. And here's something remarkable to contemplate. Other observers on planets around other stars and other galaxies see their own cosmic microwave background. They have their own surface of last scattering, a sphere centered on them at the same radius we measure but in different directions. The CMB photons they detect came from different parts of the universe than the ones we detect. The universe is so large that each observer sees a unique portion of the last scattering surface. Our view and their view overlap, but they're not identical. This means there's more universe beyond what we can see. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is finite, but the universe itself could be infinite, extending beyond our observable horizon, though we cannot know for certain. If the universe is indeed infinite, it would contain regions we will never be able to see, no matter how long we wait or how powerful our telescopes become. The cosmic microwave background defines the edge of our observable universe, but it doesn't necessarily define the edge of the universe itself. There's something both wonderful and melancholy about this. Wonderful because it suggests the universe is even larger and more magnificent than we can directly observe. Melancholy because it means there are parts of reality we will never access, regions of space disconnected from us by the fundamental constraints of cosmology, forever beyond our ability to study or explore. The cosmic microwave background also changes our perspective on time. Human lifetimes are measured in decades. Civilizations last centuries or millennia. The Earth has existed for about 4.5 billion years. The universe has existed for more than 3 times longer than that. When we detect the cosmic microwave background, we're receiving information that left its source before the Earth existed, before the Sun formed, before most of the stars in the Milky Way had been born. The photons we detect are older than almost everything in our cosmic neighborhood. And yet, the universe continues. The expansion persists. Right now, even as we observe the cosmic microwave background from 13.8 billion years ago, new photons are being scattered in distant parts of the universe. The surface of last scattering continues to exist, moving farther away as time passes and the universe expands. Cosmic microwave background photons that were scattered in our vicinity during recombination have long since passed by and are now traveling through space far from here, perhaps being detected by observers in distant galaxies, carrying to them information about the conditions in our region of space when the universe was young. The universe is dynamic, ever-changing, yet the physics remains constant. The same laws that governed the behavior of the primordial plasma also govern the behavior of matter and radiation today. The cosmic microwave background is evidence of this consistency, this reliability of natural law across billions of years and billions of light years. We can understand the early universe because the same physics applies there as applies here. This is perhaps the most fundamental assumption of science, that the universe is comprehensible, that patterns exist and can be discovered, that the laws of nature are universal, and the cosmic microwave background confirms this assumption in the most profound way. Good night from the edge of time. As we come to the end of this exploration, let's bring it back to where we started. Close your eyes again if you feel comfortable doing so. Imagine yourself floating in space, surrounded by darkness, but now with the knowledge of what fills that darkness, the faint microwave glow permeating every cubic centimeter of the universe, the ancient photons traveling for more than 13 billion years, bringing with them stories of creation, echoes of the Big Bang, signatures of the processes that gave birth to everything we know. You can't see this light with your eyes, but it's there, right now as you listen to these words, as you rest wherever you are. Billions of cosmic microwave background photons are passing through your body every second. They've traveled across most of the history of the universe to reach you. They carry information about a time when there were no stars, no galaxies, nothing but cooling plasma gradually becoming transparent, liberating light to travel freely for the first time. The cosmic microwave background is the oldest light in the universe, and it surrounds us always, a constant reminder of where we came from, of the grand cosmic story of which we are a small but significant part. Understanding it has been one of humanity's great achievements, a triumph of scientific curiosity and technological ingenuity, of theoretical insight and observational precision. From a chance discovery involving pigeons and a repurposed antenna to exquisitely detailed maps made by space-based observatories, from the first confirmation that the universe had a beginning to precise measurements of its age, composition, and geometry, the cosmic microwave background has transformed our understanding of existence itself. And the story continues. New experiments are being planned and built. New instruments with greater sensitivity and finer resolution are being designed. The search for primordial B-mode polarization continues, seeking direct evidence of cosmic inflation and gravitational waves from the first moments after the Big Bang. Scientists are developing techniques to extract even more information from the patterns in the CMB, to constrain theories of fundamental physics, to test our understanding of dark matter and dark energy, to explore the nature of reality at its most basic level. The universe has been generous in giving us this gift, this cosmic time capsule, this photograph of the infant universe preserved in microwave radiation. We've learned to read the photograph, to interpret its features, to extract meaning from its patterns. And in doing so, we've discovered that we live in a universe that began nearly 14 billion years ago, that expanded from an incredibly hot, dense state that contains both matter and mysterious dark components we don't yet understand, that is accelerating its expansion under the influence of dark energy, that had tiny density variations that grew into the magnificent cosmic structure we observe today. This is not abstract knowledge. This is the story of where you came from. The atoms in your body were formed in stars that condensed from gas clouds that formed in galaxies that grew from density fluctuations we can see in the cosmic microwave background. You are literally made of stardust, and the stars themselves were made possible by the patterns in the ancient light. You exist because the universe had the properties it did at recombination, because the Baryon acoustic oscillations created seeds for structure formation, because gravity and physics and time all conspired to create conditions where matter could clump and stars could form and planets could coalesce and life could emerge. The cosmic microwave background tells us we are part of something vastly larger than ourselves, a cosmic story that began long before we existed and will continue long after we're gone. It tells us the universe is comprehensible, that nature follows laws we can discover and understand, that curiosity and patience and careful observation can reveal the deepest secrets of existence. It tells us that even the most profound questions, where did the universe come from? How old is it? What is it made of? What will happen to it? Can be answered, at least in part, if we look carefully enough and think deeply enough. And perhaps most importantly, it tells us that we are fortunate to exist at a time when these discoveries are possible, when the ancient light is still detectable, when the evidence for our cosmic origins is spread across the sky waiting to be observed. Billions of years from now, the cosmic microwave background will be too cold to detect with any technology. The evidence for the Big Bang will have faded, but we live now in this special epoch when cosmology is not just possible but flourishing, when we can look back to the beginning of time and see the universe as it was in its youth. So rest now, if you're ready for sleep. Let these ideas settle into your mind like snow falling softly on a quiet night. The universe is vast and ancient and filled with wonders beyond counting. The cosmic microwave background is one of those wonders, perhaps the greatest of all, a window to creation itself, still glowing faintly in the darkness, still carrying its message across billions of years, still whispering to us about the moment when light was set free and time began its long march toward the present. Thank you for joining me on this journey to the edge of time, to the surface of last scattering, to the oldest light in the universe. If you enjoyed this exploration of the cosmic microwave background and the profound questions it helps us answer, please consider subscribing to the channel and liking this video. It helps me create more content like this, more deep dives into the wonders of the cosmos, more opportunities to explore together the nature of reality and our place within it. Until next time, sleep well, dream deeply, and remember that you are connected to the cosmos in ways both subtle and profound, through chains of causation stretching back to the very beginning. Good night, and thank you for your curiosity, your attention, and your sense of wonder about this magnificent universe we call home.